Chapter 15 of Astronomy, the Science of the Heavenly Bodies, by David Todd. After Newton. We have said that practically all the motions in the solar system have been accounted for by the Newtonian law of gravitation. It will be of interest to inquire into the instances that led to qualification of this absolute statement. One relates to the planet Mercury, whose orbital path round the Sun is the most elliptical of all the planetary orbits. This will be explained a little later. The Moon has given the mathematical astronomers more trouble than any other of the celestial bodies, for one reason because it is nearest to us, and very minute deviations in its motion are therefore detectable. Halley it was who ascertained 2 centuries ago that the Moon's motion round the Earth was not uniform, but subject to a slight acceleration which greatly puzzled Lagrange and Laplace, because they had proved exactly this sort of thing to be impossible, unless indeed the body in question should be acted on by some other force than gravitation. But Laplace finally traced the cause to the secular or very slow reduction in the eccentricity of the Earth's own orbit. The Sun's action on the Moon was indeed progressively changing from century to century in such manner as to accelerate the Moon's own motion in its orbit round the Earth. Adams, the eminent English astronomer, revised the calculations of Laplace and found the effect in question only half as great as Laplace had done. And for years, a great mathematical battle was on between the greatest of astronomical experts in this field of research. Adams, in conjunction with Delaunay, the greatest of the French mathematicians a half-century ago, won the battle insofar as the mathematical calculations were concerned. But the Moon continues to the present day her slight and perplexing deviation, as if perhaps our standard timekeeper, the Earth, by its rotation round its axis, were itself subject to variation. Although many investigations have been made of the uniformity of the Earth's rotation, no such irregularity has been detected, and this unexplained variation of the Moon's motion is one of the unsolved problems of the gravitational astronomer of today. But we are passing over the most impressive of all the earlier researches of Lagrange and Laplace, which concern the exceedingly slow changes, technically called the secular variations, of the elements of the planetary orbits. These elements are geometrical relations which indicate the form of the orbit, the size of the orbit, and its position in space, and it was found that none of these relations or quantities are constant in amount or direction, but that all, with but one exception, are subject to very slow or secular change or oscillation. This question assumed an alarming significance at an early day, particularly as it affected the eccentricity of the Earth's orbit round the Sun. Should it be possible for this element to go on increasing for indefinite ages? Clearly, the Earth's orbit would become more and more elliptical, and the Sun would come nearer and nearer at perihelion, and the Earth would drift farther and farther from the Sun at aphelion, until the extremes of temperature would bring all forms of life on the Earth to an end. The refined and powerful analysis of Lagrange, however, soon allayed the fears of humanity by accounting for these slow progressive changes as merely part of the regular system of mere oscillations, in entire accord with the operation of the law of gravitation, and extending throughout the entire planetary system. Indeed, the periods of these oscillations were so vast that none of them were shorter than 50,000 years, while they ranged up to 2 million years in length. Great clocks of eternity which beat ages as hours beat seconds. About a century ago, an eminent lecturer on astronomy told his audience that the problem of weighing the planets might readily be one that would seem wholly impossible to solve. To measure their sizes and distances might well be done, but actually to ascertain how many tons they weigh, never. Yet, if a planet is fortunate enough to have one satellite or more, the astronomer's method of weighing the planet is exceedingly simple, and all the major planets have satellites except the 2 interior ones, Mercury and Venus. As the satellite travels round its primary, just as the Moon does round the Earth, 2 elements of its orbit need to be ascertained, and only 2. First, the mean distance of the satellite from its primary, and second, the time of revolution around it. Now it is simply a case of applying Kepler's third law. First, take the cube of the satellite's distance and divide it by the square of the time of revolution. Similarly, take the cube of the planet's distance from the Sun and divide by the square of the planet's time of revolution round him. The proportion, then, of the first quotient to the second shows the relation of the mass, that is the weight, of the planet to that of the Sun. In the case of Jupiter, we should find it to be 1050, in that of Saturn, 3500, and so on. The range of planetary masses, in fact, is very curious, and is doubtless of much significance in the cosmogony, with which we deal later. If we consider the Sun and his 8 planets, the mass or weight of each of the 9 bodies far exceeds the combined mass of all the others which are lighter than itself. To illustrate, suppose we take as our unit of weight the 1/billionth part of the Sun's weight. Then the planets in the order of their masses will be Mercury, Mars, Venus, Earth, Uranus, Neptune, Saturn, and Jupiter. According to their relative masses then, Mercury, being a 5/millionth part the weight of the Sun, will be represented by 200. Similarly, Venus, a 425,000th part, by 2,350, and so on. Curious and interesting it is that Saturn is nearly 3 times as heavy as the 6 lighter planets taken together, Jupiter between 2 and 3 times heavier than all the other planets combined, while the Sun's mass is 750 times that of all the great planets of his system rolled into one. All the foregoing masses, except those of Mercury and Venus, are pretty accurately known because they were found by the satellite method just indicated. Mercury's mass is found by its disturbing effects on Encke's comet whenever it approaches very near. The mass of Venus is ascertained by the perturbations in the orbital motion of the Earth. In such cases, the Newtonian law of gravitation forms the basis of the intricate and tedious calculations necessary to find out the mass by this indirect method. Its inferiority to the satellite method was strikingly shown at the observatory in Washington, soon after the satellites of Mars were discovered in 1877. The inaccurate mass of that planet, as previously known by months of computation based upon years and years of observation, was immediately discarded in favor of the new mass derived from the distance and period of the outer satellite by only a few minutes' calculation. In weighing the planets, astronomers always use the Sun as the unit. What then is the Sun's own weight? Obviously, the law of gravitation answers this question, if we compare the Sun's attraction with the Earth's at equal distances. First, we conceive of the Sun's mass as if all compressed into a globe the size of the Earth, and calculate how far a body at the surface of this globe would fall in 1 second. The relation of this number to 16.1 feet, the distance a body falls in 1 second on the actual Earth, is about 330,000, which is therefore the number of times the Sun's weight exceeds that of the Earth. A word may be added regarding the force of gravitation and what it really is. As a matter of fact, Newton did not concern himself in the least with this inquiry, and says so very definitely. What he did was to discover the law according to which gravitation acts everywhere throughout the solar system. And although many physicists have endeavored to find out what gravitation really is, its cause is not yet known. In some manner as yet mysterious, it acts instantaneously over distances great and small alike, and no substance has been found which, if we interpose it between two bodies, has in any degree the effect of interrupting their gravitational tendency toward each other. While the Newtonian law of gravitation has been accepted as true because it explained and accounted for all the motions of the heavenly bodies, even including such motions of the stars as have been subjected to observation, astronomers have for a long time recognized that quite possibly the law might not be absolutely exact in a mathematical sense, and that deviations from it would surely make their appearance in time. A crude instance of this was suggested about a century ago, when the planet Uranus was found to be deviating from the path marked out for it by Bouvet's tables, based on the Newtonian law. And the theory was advocated by many astronomers that this law, while operant at the medium distances from the Sun where the planets within Jupiter and Saturn travel, could not be expected to hold absolutely true at the vast distance of Uranus and beyond. The discovery of Neptune in 1846, however, put an end to all such speculation, and has universally been regarded as an extraordinary verification of the law, as indeed it is. When, however, Leverrier investigated the orbit of Mercury, he found an excess of motion in the perihelion point of the planet's orbit, which neither he nor subsequent investigators have been able to account for by Newtonian gravitation, pure and simple. If Newton's theory is absolutely true, the excess motion of Mercury's perihelion remains a mystery. Only one theory has been advanced to account for this discrepancy, and that is the Einstein theory of gravitation. This ingenious speculation was first propounded in comprehensive form nearly 15 years ago, and its author has developed from it mathematical formulae which appear to yield results even more precise than those based on the Newtonian theory. In expressing the difference between the law of gravitation and his own conception, Einstein says, begin quote, "Imagine the Earth removed, and in its place suspended a box as big as a moon or a whole house, and inside a man naturally floating in the center, there being no force whatever pulling him. Imagine further this box being, by a rope or other contrivance, suddenly jerked to one side, which is scientifically termed difform motion, as opposed to uniform motion. The person would then naturally reach bottom on the opposite side. The result would consequently be the same as if he obeyed Newton's law of gravitation, while in fact there is no gravitation exerted whatever, which proves that difform motion will in every case produce the same effects as gravitation. The term relativity refers to time and space. According to Galileo and Newton, time and space were absolute entities, and the moving systems of the universe were dependent on this absolute time and space. On this conception was built the science of mechanics. The resulting formulas sufficed for all motions of a slow nature. It was found, however, that they would not conform to the rapid motions apparent in electrodynamics. Briefly, the theory of special relativity discards absolute time and space and makes them in every instance relative to moving systems. By this theory, all phenomena in electrodynamics, as well as mechanics, hitherto irreducible by the old formulae, were satisfactorily explained." End quote. Natural phenomena, then, involving gravitation and inertia, as in the planetary motions and electromagnetic phenomena, including the motion of light, are to be regarded as interrelated and not independent of one another. And the Einstein theory would appear to have received a striking verification in both these fields. On this theory, the Newtonian dynamics fails when the velocities concerned are a near approach to that of light. The Newtonian theory, then, is not to be considered as wrong, but in the light of a first approximation. Applying the new theory to the case of the motion of Mercury's perihelion, it is found to account for the excess quite exactly. On the electromagnetic side, including also the motion of light, a total eclipse of the Sun affords an especially favourable occasion for applying the critical test, whether a huge mass like the Sun would or would not deflect toward itself the rays of light from stars passing close to the edge of its disk or limb. A total eclipse of exceptional duration occurred on May 29, 1919, and the two eclipse parties sent out by the Royal Society of London and the Royal Astronomical Society were equipped especially with apparatus for making this test. Their stations were one on the east coast of Brazil and the other on the west coast of Africa. Accurate calculation beforehand showed just where the sun would be among the stars at the time of the eclipse, so that star plates of this region were taken in England before the expeditions went out. Then, during the total eclipse, the same regions were photographed with the eclipsed sun and the corona projected against them. To make doubly sure, the stars were a third time photographed some weeks after the eclipse, when the sun had moved away from that particular region. Measuring up the three sets of plates, it was found that an appreciable deflection of the light of the stars nearest alongside the sun actually exists, and the amount of it is such as to afford a fair, though not absolutely exact, verification of the theory. The observed deflection may of course be due to other causes, but the English astronomers generally regard the near verification as a triumph for the Einstein theory. Astronomers are already beginning preparations for a repetition of the eclipse program with all possible refinement of observation, when the next total eclipse of the sun occurs, September 20th, 1922, visible in Australia and the islands of the Indian Ocean. A third test of the theory is perhaps more critical than either of the others, and this necessitates a displacement of spectral lines in a gravitational field toward the red end of the spectrum. But the experts who have so far made measures for detecting such displacement disagree as to its actual existence. The work of St. John at Mount Wilson is unfavourable to the theory, as is that of Evershed of Kodaikanal, who has made repeated tests on the spectrum of Venus, as well as in the cyanogen bands of the Sun. The enthusiastic advocates of the Einstein theory hold that, as Newton proved the three laws of Kepler to be special cases of his general law, so the universal relativity theory will enable eventually the Newtonian law to be deduced from the Einstein theory. Start quote, "This is the way we go on in science, as in everything else," end quote, wrote Sir George Airy, Astronomer Royal. Start quote, "We have to make out that something is true. Then we find out under certain circumstances that it is not quite true, and then we have to consider and find out how the departure can be explained." End quote. Meanwhile, the prudent person keeps the open mind. End of chapter 15.